So a1 to an by 2 is the first half, and an by 2 to n is the other half, right? And then we recursively call merge sort to sort each of the halves, and then we apply the merge routine, which is responsible for merging two, which is responsible for merging two sorted lists, right? So this function takes two arrays, right, x and y. The x has k elements, y has l elements, and it's supposed to, the inputs are supposed to be already sorted, right? So all you need to do is to merge them in the order, right? So if either list is empty, then you can return the other list, right? So there's nothing to do as far as merging is concerned. Now, so when you get here, that means both lists or both arrays are non-empty, and let's say, and since they are sorted, right? In this case, we are assuming that they are sorted in smallest to highest. So x1 will be the smallest element in this array, and y1 will be the smallest element in the second array. So if you want to figure out what is the first element that we need to output, then it needs to be the smallest among all of x's and all of y's, right? So we already know x1 is the smallest among x's, and y1 is the smallest among y's. So all we need to do is to compare x of 1 and y of 1, and whichever is smaller we output, and then we still have, the merge of the remaining things left, right? So if x happens to be smaller, we output x, and then we call merge recursively on what is left of x and all of y. If this is not true, which means that y1 is less than x1, which means that we have to output y first. So y1 we output, and then we call merge recursively, right? So simple, right? So there's any questions? Okay, so merge is simple, and presumably we don't have to sit down and analyze the complexity of merge. It's pretty clear that it has linear time complexity, right? So the easiest way to convince yourself is each time you execute the body, it takes constant time, right? There's only a fixed number of instructions. There are no loops except for recursive call, right? So with recursive call, we'll account separately. So if you just execute the body once, it takes you, it uses up constant time, and you output one element, right? So each time you execute the body, you're going to output one element. So which means that if there are n elements in the input, then you're going to execute the body n times, and therefore the time spent is O of n, right? So that's very clear for merge. So let's go back to merge sort and try to understand how merge sort works, and also what is its complexity. Okay? So to understand how merge sort works, let's start with this list. To right, so the very first call, let's say this is the initial array, right? This list consisting of 8 elements. So at the very top level, this is the array that we want to sort. So we are going to call merge sort on this array, and since I don't want to write merge sort every time, I'll abbreviate it as MS. Okay? So I call MS, and you can see that what it does is it calls MS recursively on the two halves of the, right? So you have right? And now this one is going to call and so on, right? So ultimately, you will end up with merge sort on single element lists, right, or single element arrays, right? So that is what is shown here. So you have gone on to calling merge sort on each of the elements with themselves, and if you look at the base case for merge sort, it just says if the base case is the else clause here, right, it simply returns the input array. So when you call merge sort of 10, this is going to just result in the input list array being returned. So you ended up with this at the leaf level, right? So after the merge sort on the leaves return, you're going to call the merge at the next level, right? So in this case, right, so what we're going to do here is we are basically at each level, we are invoking merge right? So we're going to merge the array 10 and array 2 and 5 and 3 and so on, right? So we merge these two, and if you go through the body of merge, it compares the first two elements, right? And this happens to be smaller, so it's going to output that element, right? And after outputting that element, it's going to call itself recursively, right? So we are talking about right? And this will result in 10, comma, or in the notation of the using the algorithm, where we use a circle to denote list concatenation, right? So we have 10 followed by merge of empty, comma, 2. And whenever we merge the empty list with anything else, it's going to return the list itself. So we get 10, comma 2, right? I'm sorry, 2, comma 10. Why did you tell me before? Okay, 2. Right? So the same way 5 and 3 are merged into 3, 5, 7, 3, 13 are merged this way, and 1, 6 is merged this way. And then again, you call merge at this level, and then you compare the first two elements, you get 2, and then you have 10 and 3, 5. You compare the first element of 10 with the first element of 3, you get 3, and you output that. Now you have 10 and 5, compare those two, you get 5, and then 10. So, so that's how, and you keep doing that, and ultimately you end up with a sorted list, right? Pretty straightforward, right? So let's look at the time complexity, right? So how it works is fairly easy to understand. Let's try to understand how much time it takes, right? So we have already said merge A comma B takes time that's linear in the size of A plus size of B, right? So you merge two arrays, then to do that it takes time linear in the sizes of the input arrays, okay? So given that, we can write so we can write the recurrence relation T of n, right? So T of n standing for the time needed to sort an array of size n, right? So this T stands for time, and n stands for the size of the input, right? So T of n equals, right? So you go back to the definition of merge sort, So we are going to call merge sort on half of the list, right? So, and we're going to do that 2 times. So we have 2 times T of n by 2, right? So we have divided the list into 2 halves, so it's n by 2, right? So 2 times T of n by 2, plus we need to do the merge, right? So right, so this is what we can write down, okay? In practice, when you are doing arithmetic on or simplifications, instead of writing down O of n, if you do that, you might, make mistakes in the calculation. So just write it as some k times n, or let's say c times n. Let me use c because, okay, so c times n. Okay, so the question is, what is the solution to this equation? And in general, you of course know the answer because you've seen this before. So the question is, let's, instead of just asking for the answer for this specific problem, let's take something more general, right? Which is T of n equals a times T of n by b plus O of, again, let me just write this, some c times n power d, okay? Okay, so although in this particular algorithm, a equals b equals 2 and d equals 1, right? So, but in general, when you have a divide and conquer algorithm, you could have a recurrence that's a little bit more general. So what we want to do is we want to capture the general structure of the recurrence relation and try to solve it once for all, so that you can, have the solution to that and apply it whenever you need to. Okay, so how do we solve this? So there is this Master Theorem, which is very handy, which basically takes this and tells you that there are essentially 3 solutions based on the relative values of a, b, and d. Okay, it says that if b is greater than log b to a, then it is order of n to the power d, which basically says you can ignore the recursive term, right? It says that if d is greater than log b to a, then it says that this term is going to dominate and you can sort of ignore, right? That's what it says. This one says that if d is less than log b to a, right, then you can basically ignore this term and just, deal with that term. So what you'll be ending up with is a term that just has a raised to some exponent, right? So that's this case. And then what if the 2 terms are compatible, right? So d equals log b to a, so then it says that it's a n to the power d log n algorithm. Okay? So now you can of course remember this. Master Theorem is quite handy, and if you have an exam, you don't have to solve this each time. But let's try to understand how the Master Theorem comes about. Okay? So I know that some things are too small to see. So basically what we have done is we have drawn out the recursion tree. Right? So if you think about merge sort, so at the root is the merge sort of the entire array, and then we divide that into b parts. Right? So if you look at this recurrence relation, what it is saying is that the divide and conquer algorithm is dividing the input into b parts, right? And then it's going to apply the same algorithm on each of the n by b parts, right? So that's why you have n by b at the second level, right? Or rather, you have b instances at the second level, and the problem instance is of size n by b, right? No, I'm sorry. Okay. Okay, so here's A and there's B, right? So what this says is, So at the root, you have T of n, right? At the next level, you have A times T of n by b, right? So you have A instances, each of size n by b. Okay, so I confused you before, but so at each level, we divide up the problem into instances of size n by b, but there are A such instances. Okay, so you have A instances at the first level, A squared instances at the second level, and all the way here, right? You have some A to the power k, right? So you have some A to the, after a depth of k, then you have A to the power k elements here at the leaf level, right? Now we know that since you have a B-way branching, right? This is a B-way branching tree, therefore we know that the depth is going to be log b to n, right? Because you start with n elements, you have n by b squared, right? And all the way, right? So when you have such a tree, its depth is going to be log b to n, right? So in the case of binary tree, of course, you know, if you get confused, just substitute b equal to 2, and then you immediately recognize it and say, yeah, this, you know, a binary tree has depth which is log n, right? So if you have a b-way branching, then the depth will be log b to n. Okay, so that is the depth. Okay, and so we have A-way branching, right? So the branching factor is A at each level, right? So we have so if you take this down and write out this equation and then say, okay, at each level, right, this tells you the work that is done at that level, right? And this term represents the work done at the children, right? So if you look at this, at the very first level, n to the power d is the work done in order to, at this level, and then you have A instances of the problem, right? So this term represents, okay, and this term represents work done at this level, right? So what we are going to do is, in order to sum this up, we are going to write out the work that is done at each level, and then we will sum that up, right? So at the root level, we have n to the power d, correct? That is the work that is done at the root level. Then the rest of the term is just at the child level. Okay, so at the child level, what are we doing? We have A-way branching, right? And we are working with lists of the size n by b, right? So the work done at this level is going to be n by b whole power d, right? So we are going to have right? Okay. And then we're going to have, at the next level, we're going to have A squared right? And so on. Okay? Now, all the way to A power log b to n. Again, we're just substituting the fact the depth is log b to n, therefore, after branching through so many times, you will have a to the power log b to n instance, right? So this, and then at the leaf level, the cost is 1, right? So we don't have any more work to do, right? At the leaf level, we have just a list of single element. You know, it takes only constant time to do the work, right? So basically what we need to do, right? So this is the work done at the root level. This is the work done at this level. This is the work done at this level, and so on, right? So all we need to do is we need to add this up, and then we'll get the answer, okay? So now, we won't add it up, but instead we'll just make a few observations from which we can fairly easily understand the formula that we have in the previous case, okay? So, notice that from the definition of log, a to the power log b to n is the same as n to the power log b to a. Okay, so why is that? Let's just, or let's, for the moment, you know, take it as a given, and we will okay, so log b2 n equals n to the power log b to a. Okay, so take this for granted. It's a fairly simple manipulation on logarithms to get to that. So now what you have here is something like a geometric series, right? So you have something increasing by a factor of, you know, you are multiplying by a and dividing by b to the power something, right? So now let us, so we can write this down in the following way, right? So we can take n to the power d, and then what we are going to do is we are going to write this down as n to the power d multiplied by a by b to the d, right? And this one is again n to the power d divided by a by b to the power d squared, correct? N to the power d, if you take, right? So you can do the math, right? So n to the power d, the denominator is b to the power 2d, and you get b to the power 2d again, right? The numerator is a squared, numerator is a squared, right? So if you go through all of this, then let's write down the last but one step, which is a to the power log b to n minus 1 times n divided by b to the power So you can see that this is a geometric series, right? And now what you can say, and then with the last term, which is a to the power log b to n, okay? So now you can ask the question, what is a, if a is greater than b to the power d, okay, that means this is an increasing geometric progression, right? So, because again, what you're doing is n to the power d, and then you're multiplying that by a by b to the power d and something else, right? So if this is greater than 1, then this term, which is obtained by simply multiplying this term by a by b to the power d, right? So the whole thing is a geometric progression with ratio a by b to the power d, right? So if this happens to be greater than 1, or in other words, a greater than b to the power d, then this term will be greater than this term will be greater than this term, and so on. So the term that will dominate, therefore, is the very last term, right? So essentially what we are saying is that the cost of this level is much larger than the cost of that level, and then the cost at this level is much larger than that, and so on. And all the way we get to the leaf and then say, okay, that is the dominating cost. Okay, so what is the dominating cost at the leaf? It is a to the power log b to n, which means that is the same as n to the power log b to a. And sure enough, right, the Master Theorem says is the answer says if b is less than log b to a, then this is the result, right? So let's just work through this condition and figure out exactly what this means, right? So if a greater than b to d, b to the power d, then you can take logarithm to the base b on both sides, right? So that means log b to a greater than b, right? So we take log to the base b, you get a b here, and log to the base b, so we get log b to d. So when this condition is satisfied, you have an increasing geometric progression. So the sum is going to be really given by the last term, or it's going to be of the order of the last term, and therefore you get the answer a to the power log b n, which is x to the power log b a. So your Master Theorem says that b is less than plus b a, right? B is smaller than log b a, then the Master Theorem says you just go to log b a, right? Now let's take the other case where a is or b to the power d is greater than a, which means that b is greater than log b to a, which means that it is decreasing geometric progression, right? So in a decreasing geometric progression is the first term that's going to dominate, right? And that's why the Master Theorem says that if b is greater than log b to a, then your answer is right? Now, if both sides are equal, right, then you cannot say one dominates over the other. So essentially you have to add up all the levels, right? So because at each level you have, because we said at each level it's the same, right? So it's going to be n to the power d at each level. Therefore you have log n levels, so you have the middle formula here, which is n to the power d multiplied by log n. So all the three cases are actually pretty easy to understand, right? By following this picture, writing down the cost of performing each level, and then looking at the geometric progression, arguing about the different cases of falling, or increasing or decreasing geometric progression, or constant value of geometric progression, and then you get those three cases, you solve them, and you get the answer. Okay? So let's see. Of course, this is not the sometimes. So in a divide and conquer algorithm, very often you will get a recurrence relation that matches this Master Theorem. You can apply it, and then you will immediately have a closed form solution for time complexity. Right? But there are other times when it doesn't fit this form, in which case your best bet is to guess and check. Right? So you can guess, and then you can try to prove by induction. Right? Once you can guess, then you can always prove by induction that your guess is right, assuming your guess is actually right. Right? So that's what you do if it doesn't fit the this Master Theorem. So there are also other techniques for solving these divide and conquer type of problems.